Hey, welcome to The Explainer. Today we're going to tackle a classic machine learning challenge. How do you draw the single best line to divide two groups of data? Well, the answer lies in a really powerful tool called a support vector machine.
Okay, so let's just jump right in with a puzzle. Take a look at these two clusters of dots, the reds and the blues. If you had to draw just one single line to separate them, where would you draw it?
I mean, you could draw a line right here. And yeah, technically it works. All the blues are on one side, all the reds are on the other. But it feels a little tight, doesn't it? It's really hugging those blue dots. Okay, what if we tried this instead? We could slide it over here. And again, it perfectly separates the data, but now it's getting kind of uncomfortably close to the red cluster. You know, if a new red dot showed up nearby, it might land on the wrong side.
So you see the problem, right? Lots of lines can do the job, but we're not just looking for any line. We're on a hunt for the single best, most robust, and most confident line we can possibly find. And that is exactly the problem that this really powerful machine learning algorithm called a support vector machine, or SVM for short, is built to solve. It is all about finding that one optimal boundary.
The whole idea behind an SVM is actually super simple and kind of elegant. It says the best boundary isn't just a line. It's the line that creates the widest possible street, or margin, between the two groups. A bigger margin means more confidence.
Okay, so how does it actually do it? How does an SVM find this widest street? Well, it all boils down to three key ideas: the hyperplane, the margin, and these things called support vectors. First up, in the world of SVMs, we don't just call it a line. That's a bit too simple. It's called the hyperplane. Now, in 2 dimensions like this, it is a line. But in 3D, it's a flat plane, and in even higher dimensions, it's a hyperplane. This is our final decision boundary.
Next, you've got the margin. And that's literally our street, right? It's that empty space, that buffer zone on either side of the hyperplane. And the SVM's entire goal is to make this street as wide as it can possibly be.
And finally, and these are the real VIPs of the whole operation, we have the support vectors. These are the specific data points from each group that are closest to the hyperplane. They're the ones sitting right on the edge of that street, and they're what support the whole thing. They define where that boundary has to go.
Okay, this is where things get really cool. Because in the real world, data is messy, right? It's never this clean. So what happens when perfect separation just isn't possible? Like, what if you have an outlier? Take a look at this. We've got one blue dot that's gone rogue. It's deep in red territory. A really strict perfect rule would get completely thrown off by that one point. And this is where SVM is so clever. It gives you a choice. You can use a hard margin, which is a total perfectionist. No mistakes allowed, period. That makes it really sensitive to outliers. Or you can use a soft margin, which is way more realistic. It aims for the best overall separation, even if it has to let 1 or 2 points be on the wrong side.
So with a soft margin, the SVM is smart enough to say, you know what? I'm going to ignore that one weirdo blue dot. It knows that by sacrificing perfection on that single point, it can create a much better, much more sensible boundary for everything else. It finds a line that will probably work better in the long run.
But wait, there's more. SVM has this other incredible trick up its sleeve for when the data looks completely impossible to separate with just a straight line.
It's called the kernel trick, and it's brilliant. So the problem in step 1 is that your data is all mixed up. There's no way you can draw a single straight line to separate the reds from the blues. But here's the trick in step 2. A special kernel function performs some mathematical magic, projecting the data into a higher dimension. And the solution in step 3 is that in this new dimension, bam! Suddenly, they're perfectly separable. It's an incredibly clever way to find a simple solution to a complex-looking problem.
Okay, so after all that, the big practical question is, when should you actually use a support vector machine? Well, it's got some huge advantages. For one, it's awesome when you have tons of features, like an image classification. It's also a champ at handling those messy, non-linear problems, thanks to that kernel trick. Plus, as we just saw, it's tough against outliers when you use a soft margin. And because the final model only depends on those few support vectors, it's super memory efficient. But, of course, it's not a silver bullet. If you've got a massive dataset, training can be super slow. Picking the right kernel and tweaking all its settings can be a real headache. And sometimes it can feel a bit like a black box. It gives you a really accurate answer, but good luck figuring out exactly why it made that decision.
So we've seen how SVM is this incredible tool for finding the sharpest, clearest boundary possible. But that leaves us with this one last thought to chew on. What happens if the most important story isn't about the separation at all, but about what's happening in the messy overlap?